Let me say this different. Today is interesting. You get to learn how to do something you've never done before. So, yes, hard is right. I think this is going to be hard for some of you. But I also want to be very clear. We've done a bunch of things that were more or less the same thing over and over again. We're going to calculate the flux. This one thing is changing, and we're going to use this one thing that is changing to figure out the EMF. And we're going to have this whole spaghetti soup equation when we're done. Spaghetti soup. Alphabet soup equation when we're done, where letters are everywhere. We don't really care how they got there, but it kind of makes sense if you talk about the letters, right? That's what we had the last couple of days. But there was nothing particularly interesting. Yes, we found out that if you take a loop of wire and you shove it into a place with a magnetic field, the faster you put it in there, the bigger the EMF. That stuff like that is making sense. The faster you rotate the loop, the more EMF you can get. These things make sense, but when it comes to the actual calculations, we haven't had to do anything particularly interesting. This one has something interesting, and it actually speaks to a question that I've had from a couple of students in the last couple of days, all about the same thing. We're calculating flux, and while calculating flux, we are freezing time for that instant. And so some of you have come up to me with a very specific question, which is, okay, you calculated flux by saying the magnetic field wasn't changing, or the area wasn't changing, but it is changing. It's changing as from one moment to the next. But when we're calculating flux, we're taking an instantaneous moment, freezing it in time. The calculation of flux isn't about whether the magnetic field is changing over time. The calculation of flux is a summation where we're adding up how much magnetic field passes through an area. So as long as the same amount of magnetic field passes through an area for an instant in time, the magnetic field is constant. Now, the calculation of flux is done without consideration of particular moments in time. That's what I mean. We are freezing time for that instant. And what we're doing is we're taking our area, we're breaking it up into pieces, and we're asking ourselves some questions to see if we actually have to integrate or we don't have to integrate. With the most important question being, is the magnetic field the same everywhere within the area? Question one, which is one we've been asking a lot, is the magnetic field the same everywhere within an area? And is the angle between the magnetic field and the plane of the area the same everywhere within the area? And if those things are true, then we can immediately drop to something like b cosine theta, and then we just add up the area. That's what we've been doing. And when we add up the area, we just get the area, which means this becomes b cosine theta times the area. And a lot of times cosine theta hasn't even been there. And we didn't even care what the area was, even though I said, oh, okay, it's a loop, so it's pi r squared, but it could be a square, so it'd be side squared. We just kind of neglected some of that. Today is interesting in that we could come up with a way of calculating flux where we don't have the luxury of having the magnetic field be uniform everywhere within the space, like what I've drawn here. I have a loop of wire next to a long current carrying wire. Now, what's important about this arrangement, and let's go ahead and give us some details. Let's say that this is, let's go with a L and this W. Is that okay with you guys? Length and width. And we'll say that this is a distance Z away from the wire. Now, if I asked you to calculate the flux that's passing through this loop of wire, that's this area, I no longer have a situation in which the magnetic field is uniform everywhere within that loop. Because I know what the magnetic field is around the outside of a long current carrying wire. I assume you do too. You've got it memorized, right? If you don't, you can, of course, quickly use Ampere's law to figure it out. But who has it memorized? Who knows the magnetic field around a long current carrying wire? Does it have pi or does it not have pi? It has pi. That's right. This is the one that does have pi. If you don't believe me, Ampere's law. So we know that in this region of space, the magnetic field from the current carrying wire, that's from this wire here, is going to be mu naught I over 2 pi r, where r represents the perpendicular distance away from the wire. Now, real quick, the magnetic field direction, right? It's traveling in a circle around this wire, like so, suggesting that it is coming out of the board on this side and going into the board on that side. I just used the right-hand rule. All good for us? No? Yes? Now I'm gonna call somebody in the class out, and it's just because I'm mean today. So Andrew. It's not always Andrew. I sometimes call you out. I could call you out if you'd like. You could be next.
No. It's always me or Andrew or Aaron.
Okay, then it'll have to be Sarah. It is Gokul sometimes. Or I could pick Gladdy this time if you'd like.
It's also always, okay, well, I'm saying it's always everyone at this point.
I mean, I'm just trying. Noah, do you want to answer this question? Noah left his. We established the fact that the magnetic field is symmetrical as we go horizontally. It doesn't change as we move horizontally. But the magnetic field is symmetrical in that it's the same, here as it is over here. But also that as we move away, it reduces it the same amount as we get further and further away from the wire. All okay? All right. That means if I consider a small place inside this loop, say here, and I compare it with the same size area here, those two would not have the same amount of flux. Yes, they would not have the same amount of flux. Or no, they would not have the same amount of flux. That's a double negative, so I'm not really sure how that works anymore. Language is weird. The flux would be different between A and B. How's that? All right. So this gives us a chance to actually do something when it comes to calculating a flux, where we would actually have to do some integration. Because in this case, the flux changes as we go from one place to another. But the nice thing about it is that we have a certain amount of symmetry that will help us make doing this calculation a little bit easier. That symmetry is that if I take, say, this square, or this rectangle, and place it here, the magnetic field inside this rectangle is relatively the same everywhere from left to right within this rectangle. If I make the rectangle small enough, there would be just very little difference in the magnetic field when comparing this side with this side of the rectangle. Would everybody agree with that? It changes a small amount, but not very much, because we're just changing our distance away from the wire by a little bit. Is that okay? All right. So what I'd like to do is I'd like to show you how you calculate the flux for arrangement like this. It's not particularly tough, but it's a good example of what we would do if we had a magnetic field that wasn't uniform in a region of space where we needed to calculate the flux, and this is a good example. So let's start by considering that this red rectangle, which I've drawn in there, has an area of dA. We're going to build an integrand, and we're going to use some properties of our integrand to help us determine things like how much flux there is inside this rectangle. Now, the truth is, dA is nice, but dA doesn't tell us very much about the shape of this. We want to choose a way of expressing dA that has some variables of integration. I'll remind you that part of the thing about building an integrand is understanding things that don't change as you move from one place to another and things that do change as you move from one place to another. So the first thing I want to kind of point out is that every one of these rectangles is going to have the same width. Would you agree? And every one of these rectangles is going to have the same length. Wouldn't you also agree? I'm going to describe the length here to here in one variable and describe the width as just W. That okay? Now, one of the things that I need to remind you about, it's been a little while since we've done this, but not too long, is that we're trying to build something that we can integrate. And I hope most of you recognize that this is going to come to play here real soon. This expression is telling me the size of the magnetic field a distance r away from our wire. Does that make sense? Well, if I want to calculate the magnetic field inside this rectangle, like the entire wire rectangle that I have, it looks like r is going to have to start at a location z and will end at a location of z plus L. Does that make sense? Because my first location of my rectangle will probably be right there, won't it? And the last rectangle will be right there. So in trying to figure out how I want to express dA in terms of something that I can integrate, I probably are going to want to use variables related to how far away I am from the wire. So I'm going to define r as being the distance from the wire to where my rectangle is. I don't think that's going to be part of my my area. It's just a pointer that points to the first rectangle, the middle rectangles, and the last rectangle, right? It's going to be a temporary variable. I do, however, think that I can make dr represent the height of my rectangle, right? It's a little more in the direction of r. This way, I get a length and a width of my rectangle so that I can express the area as length times width. And I'm not writing this out to insult your intelligence. I'm writing this out because every time we've had to calculate something using an area, we've always been trying to find a product like this. And sometimes it's been more complicated than others. For the width, I'm just going to use W because that's already an established variable. And for the length, I'm going to use dr. I think that will work for a calculation of my rectangle's area, dA. Any question about where I came up with any of those? All right, let's begin to build my integrand. From here, I'm going to take away the dA and write that as dr times W. Gokul's got this confused look on his face, but I think we're okay. Before I get too far away from that, though, by taking away dA, I'm also going to have to deal with the direction of the area. I think it's not a huge thing to say that the direction of the area was in the same direction as the magnetic field. Yes. dr is a little more in the direction of r. R is the distance from the wire to where the first rectangle is or a middle rectangle is. So it is, if this will work, oops, dr would be from here to here. Does that make sense? I'm using it specifically because r is in the function for magnetic field. R represents how far from the wire we're at, so I'm sticking with variables that were in the function for the magnetic field. Now, going back to my other supposition, the area has a direction that is out of the board, and the magnetic field has a direction that is out of the board. So I think we can evaluate the dot product as being the cosine of 0 degrees. So I will eliminate the dot product, maybe, and write cosine 0 degrees as a reminder that I've eliminated the dot product and I no longer have to worry about the direction of the magnetic field and the direction of the area. That leaves just one more thing to do, and that is replace the magnetic field with something that has to do with the actual produced magnetic field from my current carrying wire. So I will rewrite the flux as the integral of mu naught I over 2 pi r times W times dr. Now I want to get the full magnetic flux through the rectangle, so I need to start at a location Z away from the current carrying wire and go to a distance L plus Z away from the current carrying wire. Where's the first rectangle and where's the last rectangle? Any questions about those choices? Better? Now, this will do the work, but the rest is just calculus. And I know you guys are good calculus students, so this part should be easy for you because this is just a procedure. So I should be able to say to you, get on it, and then pick one of you in a minute. Because almost all of you are in calculus and have done this before. So that seems like I could pick on anybody. So 60 seconds? 60 seconds should be sufficient. So Benson, I'm sure, has got it. I didn't see Benson's, though. Benson, what do you got?
I've got mu naught I W over 2 pi times ln of L plus Z over Z.
There it is. Perfect. So you've calculated the flux. Now, this part's going to be a little more difficult to deal with. So this is the flux that would be inside any kind of current loop. Obviously, calculating this for some kind of like something that wasn't perfectly rectangular would be more complicated, and we wouldn't do it. This is the limits of what they would expect for you to be able to calculate flux for this kind of situation. However, generating an EMF, there's a lot of ways to do that now. Obviously, moving this whole wire loop closer to or further away from the current carrying wire would generate a flux. Would generate a change in flux. But moving the wire makes this a hard one to deal with. Imagine if I was just going to take this wire and pull it away from the current carrying wire. So we apply a force here and start moving this with velocity v. If I ask you to calculate the EMF in the loop, that becomes very hard because of where z is and how it's changing. Not impossible, but imagine now if I said, okay, calculate the EMF by finding the rate of change of the flux. Well, suddenly z would be where the derivative is. Oops. And that would be velocity. And it's buried inside the natural log, and there's two of them. That can make for a challenging calculation, not impossible, but a challenging calculation. The more likely thing is to change the current, is to give you an expression where you calculate the flux, but then they provide you a current that's changing. That's pretty easy then, because this portion stays a constant, and it's just the current that's changing. But those are two different ways you could be expected to find an EMF in a system in which there is a interesting flux, but not necessarily a particularly interesting change in current. So they might say this equals AE to the CT or something like that. That wouldn't be a particularly, obviously, why would you have an exponentially growing current? They don't care about that part. They care about understanding that you're going to drop this in for I and then calculate the derivative. Okay, so there's been this problem on AP exams. It's not an unusual problem to be asking you on test questions. It's a good practice of how to deal with flux. But once you've seen it once, you've seen every way in which this can be done. Now, since I only have it, I do want to show you a couple of odds and ends of things I haven't talked about. And one of them is not particularly interesting, but I think it's worth discussing. imagine you have a solenoid. One of the reasons we discuss solenoids is because a solenoid will have a uniform magnetic field through the middle of the solenoid. So if we have a current passing through this wire and we have a solenoid in space, then inside here is a magnetic field that is uniform. And you understand how to calculate that magnetic field. Well, if I take another loop of wire and wrap it around the solenoid, like so. Now imagine taking this, turning it sideways, so that there's the solenoid wire, as shown. But then there is this larger loop of wire around the outside. There's clearly a magnetic flux passing through the yellow wire, correct? Because there's a magnetic field inside the region of space where the solenoid is. That magnetic field only fills the space where the solenoid is. The magnetic field outside is 0. But this loop of wire still has a magnetic flux passing inside of it. It's going to be based on the radius of the solenoid. So if that's R and this is R, little r and big R, the area of the smaller loop has an area of pi little r squared. But there's still a magnetic flux for the yellow loop that would equal B times pi little r squared. Even though the yellow wire has an area of pi big R squared, the magnetic flux through the yellow wire is only where the magnetic field is. So if this current, if this current is a function related to t, you could generate an EMF in the outer loop from the change in flux in the inner loop. You guys following that conversation? So if I have a change here, I suddenly create an EMF there. How many of you have a magnetic charger for your phone? How do you think that's working? Nobody has a MagSafe charger? Open up the back of every MagSafe charger or every Samsung charger, you're going to find coils of wire that are right there near the surface. The idea being they're going to place it next to another set of coils of wire that have a changing magnetic field. This generates an EMF inside the exposed wire. In the old days,